All right, hi. Today is our last lecture. If it will be one lecture, maybe I will split it. We'll see. But this is kind of an advanced topic and the last topic in the course, and it's about modeling those things that I promised for quite some time now. So we will basically, here are the goals for today. We will start with fixing an error that we actually did fix in the Zoom meeting. So with those of you who were in the Zoom meeting, but because not all people were there, and also I want these lectures to kind of stay online as a standalone thing. So we'll need to fix this thing, this error. And another thing, and that's the error in the very last block in the part that did the parameter sweep and looked at how many people were infected depending on the probability, I think, of disease spread. That's what we did the last time. I also grew increasingly unhappy with the state of the code in this gigantic notebook that we got. And I think so. Like there are lots of things that I wish I could change about it, but there were quite a few wrong decisions that I made as I was writing it, starting with naming the variables and down to how the code is organized and the architecture of it. But at this point, I'll probably leave most of them there. Still, I want to refactor at least this very last part to make it a little bit less annoying. And then we will actually model herd immunity, something that I promised for quite some time now. So we'll change the vaccination rate, the default vaccination rate in the population. And then I want to kind of talk a little bit about what it actually means, which may necessitate a certain tangent and fixing a certain error that only becomes obvious in the code. That only becomes obvious if you actually attempt that. And then after that, what's after that? Yeah, and then the last part, which may actually become a separate lecture, will be about assertivity, which is, as I mentioned before, perhaps it's about like nodes that are alike to each other, being more likely to be connected to each other than nodes that are not alike to each other. Well, no, well, in the most general sense, it's actually slightly different. It's actually more kind of more generalized. So if there is no assertivity, then for a certain uh, property that the node may or may not have, if there is no assertivity, then nodes that have this property and that don't have this property are equally likely to be connected to each other. Then we can have positive assertivity, in which case nodes that are connected are more likely to be alike in respect to this property, and we can have negative assertivity, and that's when nodes that are connected are more likely to be different. So if you go through the graph, you usually have like nodes, the property of this node alternating. Doesn't sound too well explained. But say like there are black nodes and red nodes, and no assertivity means that you can have no reasonable prediction about what nodes will be connected to, say, a red node or a black node. If the assertivity is positive, then most black nodes will be connected together and most red nodes will be connected together. And if assertivity is negative, then you would think that red node is mostly connected to black nodes, but each of those black nodes is mostly connected to another red node, and so on. So if you go through the graph, you'll mostly have black, red, black, red, black, red. Not necessarily always so, but more likely than not. And in our case, we will look at what happens if vaccinated people are more likely to be friends with other vaccinated people, while unvaccinated people are more likely to be friends with unvaccinated people. So we'll try to gauge what effect it would have on the propagation of disease in a pandemic, all other things being equal, right? So yeah, that's where we are. So let's try it. And first, this error. So let me first run this entire thing because Yeah, and by the way, so this is the version that we got by the end of last class. So that's not the version that I worked with in Zoom. Okay, all right. Okay, everything works. Good. So what we have here, so let's start with this error. Not the error, but mistake. Mistake. What do we have here? Here we have this code. This is the part that runs a computational experiment, and this part runs the actual experiment, and this next cell visualizes it. And what happens here is probability is stepping through different values. So probability that at each time step the disease will be transmitted from an infected node to a susceptible node that we call healthy in this model. So right now, all other parameters are set. For example, 20 steps, 100 nodes, infected period of 10. So for 10 time steps, infected node becomes infectious, stay infectious, and then they become immune. We run 100 trials, but probability goes through 10 steps from like the minimal value. That's not zero, but the minimal non-zero value is this line that takes care of that, and up to 1. And probability of 1 means that at every step, every node that connected to the infected node also becomes connected, right? So if a disease can spread along the edge, it always does spread along the edge, and that's what we got. So on the left we have number of new cases, and you can see that every day, and with the highest probability of spread, we have the sharpest peak, and it gets increasingly flatter as the disease becomes less contagious, essentially. And on the right, we have the share of population affected as a function of daily probability of contagion. So as the probability of contagion reaches 0.6 per day, yeah, these are the units. I'm not sure what the units are, but as it reaches 0.6, basically we always have a full population fully infected, right? And we don't have vaccinations yet. So one thing that one of you noticed is, okay, let me have fewer trials, is that if the infectious period is larger, so nodes stay infected for longer, actually what happens is that by the end of the simulation, not all nodes become infected. So C no longer terminates at 1, at the share of 1, at 100%. Let me make infectious period even longer, so 18 days. Look at that, barely anyone is infected now. What the heck? How is it possible? And the answer is simple. When I calculate here whether, so at the end, is it at the end? So okay, let's see. So this value comes from this total infected, because this, I'm guessing this line builds this plot, and this plot uses the average of total infected as its y, as its y variable. So total infected, let's see how it's calculated. Total infected after the pandemic was run, so this line actually runs the pandemic. So we don't have the time loop inside here, it's inside the function pandemic. So at the end, total infected equals to the count infected. And count infected is incremented by 1 every time we find an immune node. So an immune node is the node that used to be infected, used to have an infection. However, if the infectious period is 18 and we're modeling for 20 steps, most of nodes are still in the infected state. So we have to actually change this, because to calculate nodes, to find all nodes that were infected by the end of the model, we should include both nodes who are still infected and those nodes who recovered and became immune. So we need to add or val 0, whatever it is, equals, that's the value of the node, I guess it equals infected, right? Infected. So if we run it now, yep, look, it's like 100%. So we fixed everything. Now it's correct. Okay, so I mean, this looks horrible, but the plot looks really sad, but that's because infectious period is so long that everything is saturated. If we make it infectious period a little bit more reasonable again, this plot will also become more reasonable again. Good. All right, so point number first done. Point number second done. I will actually want to reuse this computational experiment as a different computational experiment. I will want to use kind of this code for trying different vaccination rates in the system, right? And for now, it's very annoying. It's written in an annoying way because everything is about probability, and the variables are called like that. So they're called prob for probability, and the counter is called iprob, and the number of steps is called nprob steps. So you know what? Let me refactor all of that. First of all, let me take this visualization and move it in here because I want to run the entire thing every time I run it. Because I use my visualization as a test also, I want to make sure that everything works. Okay, so let's actually run it as a test. Yeah, okay, so that's what I will be after. I need to see kind of these plots. But now I want to make this part kind of agnostic to what exactly parameter I change, because like this is annoying. So let me be consistent. I will call all my variables param for parameter. So instead of iprob, I will call it iparam. And I need to change this one, this one, this one. Okay, let's just go this one, this one. Nothing here, this one. And actually it's reused again in a different loop here when I plot all the curves. Tish, tish, tish. Okay, that's it, I think. So iparam done. Then prob will be probability. It's okay. So n prob steps will be called n param steps. This one and this one and this one and this one and this one. Any other parts? This one, right? Okay, so let's try to run it. I will actually do restart and run all because I want to make sure that old variables are not saved. Okay, see a name error. Yeah, because I failed to edit one of those. Nprob steps is still hiding somewhere. Where is it? It's in line 13. I press L. Okay, this one. Yeah, here you are. Okay, good. Oops. Okay, run again. Now it works. Good. So we're closer to actually running it. Good. So now, what do we do now? We are kind of closer to actually changing the share of vaccinated people, nodes, right? Okay, let's look through the entire code and see what we can. Are there any parts that we hate? Like, okay, this is a test. Degrees, yeah, we'll need degrees, random network. So this thing generates an Erdos random network. Let's remove it just because we use Barabasi network at this point. So it will stay in the older version of the script. And like in real life, I would have actually saved it and I would have made it part of this module. So I would have cut this graph thing into a module, but I just don't have any steam to do it now. So I will just delete this thing. We definitely keep the Barabasi one because that's our main working horse. Here we have some sort of alt text by alt text. Pandemics is good, test case is good. An inventor of this model, this is a very important piece of information, but you've read it already, so we delete it. Okay, so good. Everything that remains stays with us. So now let's see. So let's go and see what do we have here. So right now the pandemic thingy can be initialized with different vaccination rates. Right? Yay. Okay, let's use this because this code seems to have been already written. Oh no, yes, no, yes. Okay, so we'll use that. However, there is one more thing. So, well, let's do it incrementally. Let's start with that. Let's just code that. So pandemic, actually, the way it was written, it takes a parameter vaccination rate, and by default it's set to 0. However, here for the test case, I call it with vaccination rate of 0.1. So some nodes are actually born vaccinated. And if you look at the 0th state of this network, indeed 3 nodes out of whatever, out of 20, are born vaccinated. Good. So we can use that for a model. So let's go to our computational experiment. Let's fix probability at 0.2. Sounds good. Okay, let's change the description for the model parameter will go through that many values. Okay, so history, and history is this weird array where you have a bunch of trials and then a bunch of more trials and then a bunch of more trials to prepare for the averaging that will happen later on. So yeah, we don't want to touch any of that. Probability we don't want to do, but yeah, but now instead of probability it will be vaccination rate. So vaccination, I forgot, how did they call this vax rate? Okay, let's just use the same same spelling. It's a weird spelling, but let's use the same spelling here. So vaccination rate is zeros of number parameters. We remove this probability, but because probability is now set. But now vaccination rate for I parameter will change. So look, for probability, running a model with probability of 0, so no spread was useless because like, why? Obviously, if the disease cannot spread, then it won't spread. But running the model with probability of 1 was okay, useful, because it was the fastest spread that's possible with this time-based model that works in discrete time with like moments of time. So now with vaccination rate, the situation is kind of the opposite. Vaccination rate of 0 actually makes sense. It means no one is vaccinated, no one, because there are no vaccine available for this disease or whatever. While vaccination rate of 100% is boring because, okay, if nobody can get a disease, then nobody will get a disease. So because of that, let's make sure that vaccination rate goes not from a small value to 1, but from 0 to a large value, to almost 1. So we make vaccination rate equal to I parameter divided by number of parameter steps, because the first value that I param will take will be 0. So the first value that vaccination rate takes will be 0, and it will go to almost 1, to like n param steps minus 1 divided by n param steps. So if it's equal to 10, it will be like 90%. So the way, like with this value like that, at 10, and with this formula written like that, we'll have 10 different values of vaccination rate from 0 to 90% included. Good. So we need now to change this one line only that actually runs the pandemics thingy. So the pandemic on G, on the graph G, with probability is now a fixed value, equals probe, and steps equal n steps, infect period equals infect period, and finally vaccination rate equals vaccination rate I param, right? I think that's it. Yeah, and obviously we need to change the X label because it's incorrect. So the parameter, it's not a good, like, not for official use, but you know. Okay, let's see what it runs. Okay, so it runs, that's good. If you look on the left one, with lower vaccination rates, it actually doesn't start at it doesn't start at 0. Uh-oh. Oh yeah, because I still, look, here's a mistake. I still have probability here, prob. So this should be vax rate and this should be vax rate. Rerun. Okay, good. Okay, good. So now the left one actually makes sense, right? With lower vaccination rates, we have high peaks. With high vaccination rates, we have no cases. Like with vaccination rate of, oh, why is it still from 0.1 to 1 and not from 0 to 0.9? That's because, of course, that's because somewhere I do something incorrectly. Here, this part. Label equals probability I param. No, not probability. Vax rate. Okay, redo. Yay, now everything is correct. It runs from 0 to 0.9. Okay, so for 0.9 it's flat. No new cases. Everybody are vaccinated. Everybody are immune. For 0, it's peaky because nobody is vaccinated. The disease runs its course. So this makes sense. This one on the right doesn't, because the higher the parameter, which in this case is the vaccination rate. Okay, let me rename it. Vaccination rate. The higher the vaccination rate, the more cases we have. Why? It shouldn't be this. It shouldn't be like that. It directly contradicts the left plot. Well, you know why. That's because when we count how many people got the disease, we checked nodes got the disease, we checked whether they are immune or still infected. But immune is the state that they acquire after they recover. But it's also, if we go here in the pandemic thing, it's also the state that they are assigned when they're vaccinated, if they're vaccinated. So they're counted as if they were sick, even though they weren't. Right? So we have a mistake here. What do we do? Two options. Either we change the way it's calculated, or we just introduce a new status for vaccinated people. And the second sounds much more reasonable. So let's do that. Instead of making, so here's what happens here. If we reinitialize, so if the network status of different nodes is reset for every node, we toss a coin, an unfair coin potentially against a certain vaccination rate. And if we got like whatever is the success, so if this random number happens to be below the vaccination rate, so if it falls below, which happens with the probability of vaccination rate, then we make a vaccinated node. So instead of making it immune, let's call it vaccinated. Vaccinated. And if it's not the case, then we make it healthy, which is actually susceptible. Good. And then we need to change node propagation. So this is node propagation, I believe, right? So if the node is infectious, this part makes them immune once the infectious period is over. And here's the test of whether another node, the neighbor node, can be infected, right? So whether the disease spread onto it. And the comparison is with healthy, which is susceptible. Maybe I should rename it, but whatever. I don't want to. But we could rename it into susceptible. So yes, which means that we don't actually have to change anything about this vaccinated thing. The disease is only spread to this node, can only spread with this node because it may choose not to if the random numbers generator tells it so, but it can only spread if the other node is susceptible, which means that if it's either immune or infected already or vaccinated, the disease won't spread. Okay, good. So it looks like it should work. Let's run it. What do we have here? We have some nodes that are, most nodes are blue, and some nodes are green, and the infected node is red. Okay, good. So the only thing that worries us is that, okay, by the end of the thing, so many nodes are immune because they had the disease and recovered. But at the beginning of the simulation, some nodes are vaccinated, but they're shown in the same color. So let's go and fix that so that we can actually visually troubleshoot what's going on. So let's go back into the, where is the plotting? Here, look, we have a definition plot. So when we plot something, we just do graph, and we call a method called plot. So, and here's the if else if then block that colors it in different ways for different colors. So, and green is actually happens to be default color. So let's add an additional clause. Else if self values nodes I and 0. At this point, I barely remember what the 0 means. I think the first point, it's a tuple, and the first element is like the type of the node, whether it's vaccinated or healthy or whatever. And the second one is only makes sense for infected node, and that's the number of days since the infection. But you don't even have to remember that because there is certain symmetry, right? This looks in the same way, this looks in the same way. So this has to look in the same way too. If it's vaccinated, then colors append. Again, I barely remember what colors append mean. I can look it up in the sense that, okay, colors, what happens to colors later? Oh, look, they're given to a draw operation from network X as a vector of colors, but we can just go by analogy. So if this was colors append blue, colors append red, so we want this to be like colors append. What color will we use for vaccinated nodes? Like gray. Make it color append gray. How will it know what a gray is? Looks like a constant because all caps, so there might be a constant block. Oh, here it is. Look at red is RGB like red, blue is like that. So gray equals, like 0 is for black, 1 is for light. So let's do like 0.5, 0.5, 0.5, which is in between gray. Okay, let's test that. Well, we cannot actually test it here because we don't have vaccinated nodes. So let's test it here. Oh, look how nice. We have some gray nodes. So these gray nodes are vaccinated nodes, right? Only one here. Okay, so these two gray nodes are vaccinated nodes, and as well, no disease spread was happening. Yeah, fine. So this node was never infected, right? It stayed until the end. It stayed in the gray mode until the very end. What am I looking for? I want some really diseased. Okay, this is diseased enough. So these two gray nodes stayed gray, right? Yeah, seems to be working. It's not like a definitive test in the sense that it's not a very robust test. Maybe there may still be bugs that we either don't notice because we're doing it only visually, or that are not likely to happen because everything depends on the particular like instantiation of the network. But at least we gave it a try. It seems to be working. Okay, now with this in mind, we can go down and try to run this model actually. Okay, vaccination rate goes up, share of population goes down. Yay, we like that. So let's make the disease really bad, like probability of spread, let's make it like 0.7. No, well, whatever, 0.7 is good, 0.8. And the infectious period, let's make it like 3 days. And end trials, let's have more trials so that we have a smoother curve. Okay, let's see what we'll got. Come on. Okay. All right. So look at that. Basically, there wasn't much flattening. Yeah, the disease is so aggressive. So basically, it's just linear decrease, except for the very end. So basically, just the network becomes smaller, right? Because if you think of that, that's what happens when you have vaccinated node. The vaccinated node just cannot get sick. It doesn't get disease and it doesn't spread disease. So from the network point of view, it kind of doesn't exist, which means that vaccinating some nodes is like taking these nodes away from the network, which means that there are fewer people, fewer nodes totally to infect. There should be something subtle also happening in the sense that vaccinated nodes can block this propagation of disease, and perhaps that what leads to this like curving at the end. But overall, it's not a very interesting thing to model on its own unless we go for subtle things. So okay, let's try to amplify this subtle band by making the disease a little bit less aggressive. So instead of 0.8, let's try like 0.5, maybe even, okay, let's do 0.5 and only 2 days. Let's see whether it will make the plot more interesting. Okay, look, the band moved to the left, so that's good. There seemed to be a little bit of flattening as well. So look, it actually ran for longer. How can I make it more interesting? So let's do the following. If it's true that the longer it runs, the more interesting it looks like, let's make infectious period to let's actually ramp it up. The infectious period will be 5 days, but the probability will be even lower. So 0.2 for the probability of spread, but now it can attempt to spread for 5 days. Let's see. I'm not sure what will happen. Okay. Is it good? Is it fancy? Well, I'm not sure whether we reach the peak fanciness, but so the total number of cases goes down. Does it become flatter? Not really. Maybe that's true. Maybe it doesn't. The share of population affected goes down linearly at first, but then kind of curves. Okay, all right, good. So yay. So this was the herd immunity exercise that I promised you like 2 weeks ago, basically. And we have it now. So this is something that we can write about. All right. So let's go up and see where we are. So we are at this point. We did 3 first steps. And so the next one will be to illustrate the meaning of it. So before we go down, let me stop the video recording and then restart it so that I could spread it, split it into several videos on YouTube. So see you in the next video.